This week we have Annette Werner, and she will tell us about the birational geometry of matroids.
Yeah, thank you very much. And thank you very much for the invitation to speak here. I'm actually here as a member of the p-adic Hodge theory program, but in this members colloquium, I'm talking about another research program of mine, which has nothing to do with p-adic Hodge theory or non-Archimedean methods, but is more a combinatorial geometry project. And I also tried to keep this talk very accessible because I was told it's a general audience talk, and I tried to keep it very non-technical. Please feel free to ask questions. And I will start by setting us up in the following roadmap. So as I told you, we want to say something about the birational geometry of matroids. And actually, I think, yeah, I've not seen this terminology so much, except in my joint work with Kris Shaw. Oh, I should also say this once again. All I'm going to explain here is joint work with Kris Shaw. And we were studying the automorphism groups of Bergman fans of matroids. In order to explain you some of the things which we found there, which are very similar to phenomena in birational geometry, I'm going to start with giving you some backgrounds on matroids, mainly through many examples. I don't assume that you know anything about matroids, and I apologize to everybody who does, because I'm going to repeat some things. Then I will explain to you what the Bergman fan, or sometimes it's also called the tropicalization of this matroid is. The name fan indicates that it is a fan. We will talk about its fine fan structure and about automorphisms of the fine fan structure. And then I will try to explain to you why it is sometimes necessary to look at other fan structures on this fan. And we will study in detail an example, namely the matroid associated to the braid arrangement, or if you want, to the root system of type AN, or if you want, to complete graphs. And when we analyze the automorphism groups of this Bergman fan, through an identification with the tropical moduli space, we realize that there are more automorphisms than expected. And then I will explain why Kris and I use Cremona automorphisms to explain this phenomenon and how we generalize it to also non-representable matroids. And then I end with some examples. Okay, so that's the roadmap. And let's start with the definition of a matroid. I mean, this is a typical case. If you have not seen this definition before, this won't help at all. So this is useful for people who have half knowledge. So if you, for example, I mean, if you go to many of these talks where people always give the definition of something, it may just warp somehow in your head. But for people who have not seen a matroid, I will tell you about many examples in the next slide. So don't bother too much about the definition. But in order to be precise, a matroid is a pair of a finite set and a rank function which associates to every subset of E an integral number, non-negative integral number, which is the rank, and which is supposed to be 0 if you look at the rank of the empty set. Condition 3 says if you add one element to any given subset, the rank may jump, need not, but may jump at most by 1. And condition 2 is a certain sub-additivity property, which might be reminiscent of linear algebra when you look at dimension of vector spaces. And in fact, we will see in a minute that, yeah, you will all have seen matroids already when you consider finite sets of vectors in a vector space and take as the rank function the dimension of their span. Okay. This is a definition which is much more general. We will see that it also incorporates graphs. We do this on a later slide. First of all, with this definition alone, we can talk about things, yeah, which may also be familiar from linear algebra. We can talk about independence. Independence means the rank of a set is equal to the number of its element. And when we have a notion of independence, we have a notion of a basis, which is the maximal independent set. Matroids also have a notion of circuits. A circuit is a minimal, not independent set. So it is not independent. So the rank is smaller than the number of elements. But when you remove any one element out of it, it becomes independent. Then we can talk about flats. Flats are analogs of subspaces in linear algebra. And a flat is a subset such that you cannot increase the subset without the rank jumping. So whenever you put something in the subset, the rank will go up by 1. So it's a closedness condition, like being closed under linear expressions. Once you have flats, you can talk about closures of any subset by throwing in everything in the subset, which doesn't make the rank jump. You arise at something which we call closure, and which is the minimal flat above A. And you can also talk about morphisms or isomorphisms as usual. Take anything which respects the structure. So a set theoretic map respecting the rank. We will only need isomorphisms here. That's why I only put this as here. So don't worry so much if you cannot remember all of these things. I will recall them in examples. And I have one request. Slide talk are nice if you want to show pictures, but they have one disadvantage. I cannot point to a former board and remind you of definitions. So I would be really very obliged if you could ask me to turn back if I'm talking about anything which has just slipped out of everybody's minds. Yeah, so please just tell me, then I will just scroll back a few slides and we can have a look at the definition once more. Okay, so this is the general theory. Now to the examples everybody knows, which are called representative matrices. And they arise from finite sets of vectors in any vector space. And rank means dimension of the span, linear span of this vector. So of the minimal linear subspace of V containing those vectors. This will satisfy our conditions. That means always bigger or equal to 0. The span of the empty set is 0. This follows from the formula for a dimension of subspaces, and of course dimension increases at most 1 when you increase the set. These matrices are called representable, but they form, the representable matrices form a very negligible part in the universe of all matrices. So one has to be very careful not to jump to conclusion if something is true for representable matrices. Here, the independent subsets are just given by sets of linearly independent vectors, thus the name, and bases are bases. I mean, thus we know them from linear algebra. And if you want to talk about closures, you will just add to A every vector in this finite set E, which is contained in the linear span of A. Then you get the closure. And whenever this is equal to A, you have a flat. For the purpose of this talk, we will often assume a dual viewpoint, working with hyperplanes, which means somehow you can think about this as going to the dual space. Doesn't change much, but for me, the geometry is somewhat different. So if we have a finite hyperplane arrangement, and for our purposes later on, I always assume that they trivially intersect in some projective space, we can associate it to it, a representable matroid, taking as our subset these hyperplanes, or if you want, elements in the dual space, giving the equations. And the rank function, if you think about hyperplanes, is given, in this case, by codimension of intersection. This will be the point of view which is applicable when I later talk about matroids associated to root systems. Okay. But there is another world, mathematical universe, which somehow embeds in the theory of matroids, and this is the world of graphs. I mean, just ordinary graphs in combinatorial theory, vertices and edges. And you can associate to any graph a matroid by taking finite graphs. So I should have added that. There's also a theory of infinite matroids, but I'm not going to talk about this in my talk. For me, a matroid is always finite. So it is associated in this slide to a finite graph. by taking the edges. And then it's an easy exercise that you can recover the rank function if I tell you which subsets should be independent. And the independent subsets of the set of edges of a graph are just all subsets without cycles. So forests, which means disjoint unions of trees. So you cannot find closed cycles in these sets. Let's look at a simple example, which is relevant for our root systems later on. We take the graph, complete graph on 4 vertices. So it has 6 edges, numbered 1 to 6, and these are the elements in our ground set. Yeah. So now we can look at independent sets, for example, this and this and this. This is a tree. It's a 3-element independent subset. You cannot find a 4-element independent subset, so the rank of this graph, of this graphic matrix is 4. This, for example, is the basis. And an example of a circuit would be 1, 2, 5. So this is a dependent subset. As a cycle, but if you remove any of the 3 edges, this becomes a tree. So this is a circuit. Okay. And this gives a completely different input in the theory of Matroid, which is still also a completely negligible amount of what Matroids have to offer. Okay, but nevertheless, I will always work with simple Matroids. And simple is something which is maybe easiest to explain on graphs. So we assume that we have no loops. In Matroids, you would translate this in a general situation as having no subsets such that the rank of a 1-element set is 0. Or neither do we want parallel elements having 2-element subsets of rank 1. So 2 linear dependent subsets, so to speak. That is not a very terrible restriction, because if you start with any Matroid, you can always define a semi-simplification by just getting rid of the loops and removing one of the parallel edges. Yeah? So for us, this doesn't exist. So if you have graphs, they don't have multiple edges and they don't have loops. Okay, here's another example of a Matroid, which is in general neither graphic nor representable. You just take an n-element ground set and you declare the rank of a set as the minimum of k. This is the k be fixed, and the number of elements in A. This means that the independent subsets are all the subsets of size at most k. As soon as a subset has size k plus 1, it becomes dependent, even a circuit. If you push this to the case where n is equal to k, everything is independent with no dependent subsets. Every subset is independent, and you can think about this Matroid as being a direct sum in the theory of Matroids of n 1-element sets. And this Matroid we call totally disconnected. This totally disconnected means every subset is independent. There are no circuits and no subsets which are dependent. If you take k equal to 2, it is representable over a finite field if and only if the finite field is big enough, for example. Representable over a finite field means there is a vector space over this finite field, and there are finitely many vectors in the vector space such that the associated matroid is isomorphic to U to n. Okay, that's another example. And now we've seen enough of matroids. Let me tell you what the Bergman family object I want to study. I should maybe ask any questions so far. Any slides you want to see once more? Okay, good. Then
why are they called matroids?
Pardon?
Why are they called matroids?
Yeah, this is a good question. I'm not even sure that many people wouldn't call them combinatorial geometries. So, yeah, it is. There were several names of these objects in the literature, and I call them matroid because it's my feeling that nowadays people use this more often than they used to use combinatorial geometries. But yeah, that's the best. I'm sorry, that's the best answer I can give you. Okay. We associate now to every matroid a geometric object. And we take a simple matroid, and we do this only Otherwise, we get something which is very easy and not interesting for our purposes. If the rank is at least 2, so there are at least 2 independent elements in our set. Then we look at something which is contained in R to the E. So in this space R to the E, every element I in E gives a canonical vector. So we can now linearly combine elements in the matrix, so to speak. Yeah. And we do this by writing down something like this, for example, and checking. So I should put it the other way. So what is the Bergman fan? The Bergman fan as a subset, yeah, is defined as the set of all vectors. So this is the general element in the space. And now I want to check if this is in the Bergman fan or not. So what do? I take every single circuit in the matroid, and I check the elements, the coefficients here at the indices which are in my circuit. So my circuit has several elements, I1, I2, I3, and so on. I write down these coefficients and I have a set, or I should not maybe write it as a set, but as a tuple, and then I check, is the minimum attained twice, at least twice or not? If the minimum is attained only once, I throw it out. If the minimum is attained at least twice, this is a kind of tropical condition. I mean, if you have ever seen tropicalizations of varieties, you will not wonder so much. If not, this is just a definition. And you have to do it for every circuit. And only if vectors pass this circuit test that the minimum of the coefficients with numbers in the circuits is attained twice for each circuit, then you keep it. Yeah. Okay. Often this space is too big. One wants to projectivize in a certain way. So by this, I mean, so this minimum condition is obviously invariant under adding the same number in at every place. So you can as well divide out the line generated by the vector, by the all ones vector. We will always do this and push this subset into this quotient. And I call this the affine Bergman fan and this the Bergman fan. You always have to check where people are working. For geometry, it's often nicer to get rid of these obvious spaces or linearity spaces. Okay, so we take this subset.
When you say obtained twice, it means exactly twice?
No, at least twice. I'm sorry, this was I said it, but I didn't write it down. Yeah, at least twice. Could be constant, for example. I mean, yeah. Okay, then we push it in the quotient, and then I have a set. It might look awkward, but from people used to tropicalizing stuff, this is a very natural thing to do, because if you are a tropical geometer, you will, and you start with a hyperplane arrangement, you look at the complement of the hyperplane arrangement. This is a nice space, and this is what tropical geometers call a very affine space. So it embeds in something which we call an intrinsic torus. And from this torus, we go by taking the valuation to a real vector space, and that's the tropicalization. Okay? So this, if you do this natural tropicalization thing to a hyperplane complement, you will end up at precisely this space. This, however, has the advantage that this definition works for any matroid. I don't have to assume representability. Okay? For me, this is somehow the first geometric way I have encountered these things, but this is the definition which works for any matroid. Okay, up to now it's only a set, stupid set in some stupid vector space. Wouldn't it be interesting if we didn't have a combinatorial structure on it? And this I'm going to define now. I'm going now to define a fan structure. So we will write this space as a union of cones in a way which makes it a nice fan, namely a pure symplectic fan. In order to tell you what cones are, we need the flats. Flats are the subsets which are closed in the sense that if I try to add anything else, the rank will jump. It's the analog of all the points which are contained in a subspace in my representable picture. So for every flat, we write down the indicator vector of this flat. This means we add all the canonical vectors which correspond to elements in the flat. You can think about this as the indicator vector of the flat. And whenever we have a chain of flat or a flag of flats, when some people call it, we look at the cone, which is generated by these vectors. So all linear combinations with non-negative real coefficients. Okay, and then it's a theorem that if you do this and you push it into the Gaussian space where we got rid of the all constant vectors, then, and you do this for all chains of flats, you will also find the chains of length 1, so you will find the indicator of the flats also in this picture. Then this forms a pure simplicial fan. So all maximal dimensional simplices have the same dimension, namely dimension rank m-1. The -1 is due to the fact that we got rid of some line here. And this fan gives a fan structure on our Bergman fan. So the support of the fan is the Bergman fan. Yeah? Okay, so by looking at indicator vectors of flats and looking at cones, which are spanned by those indicator vectors where the flats form a chain, we can define the notion of cones. And it turns out, with some effort, the Bergman fan is a nice union of all those cones, yeah, in the sense that it is a fan. And we call this fan structure the fine fan structure. As we will see later on, there are other fan structures. And this is one where all the flats turn up, so to speak. Okay.
You have to put out and intersect.
No, in a fan, you can only intersect in a cone of smaller dimension.
Yes.
Yes.
But it will be a phase. Or?
Yes. Yes. You have a phase relation, which are one cone is contained in the other. I mean, if you from this chain of flats you forget one of them, you will for example get phase.
So this is for a simple M.
Yes, this is for simple M. Absolutely. Even the definition with the circlets is awkward. So this is why you, as soon as you tropicalize, go to the Bergman fan, you better assume simple. Yeah.
Is the fan complete?
No, this is the point. This is usually, it is often not complete. In interesting cases, not, of course. If you do this for the matroid UNN, you get a complete fan. This for me is not a case which I'm not so much interested in. More questions? Okay, good. So, and what Kris and I was studying is how does this fan, what does this fan know about the matrix we start with? So, I mean, if you have a matroid isomorphism, it gives a bijection between the flats, and this preserves the flag of flats. So it gives, in an obvious way, it gives you a linear automorphism of the vector space, which preserves the lattice, the all integer vectors, and preserves the curve. Yeah. The question which we wanted to answer is, okay, what about if we have any isomorphism in the sense of the Bergman fan, so coming from a linear map, linear automorphism of the ambient vector spaces and preserving the cone structures, will this come from a matroid isomorphism? And we show that it does. This is not so trivial as it might sound, because here the rays, so to speak, in this fan structure correspond to flats. And a priori, it is not so clear that the flats which only contain one element are geometrically somehow different from the flats which contain many elements. Yeah? Matroid automorphisms are you get by mapping the set E to itself, not by mapping flats to itself. Yeah? You have to preserve something like the rank in this geometry. And this is not so clear, but it turns out that if you use results by Jun Yu and his collaborators in these wonderful works on Hodge theory for matroids, that you can see by looking at certain intersection numbers you get because there's a degree function on the Turing, that you can actually tell the ranks apart of these matroids. This is really a very nice, this is really a very nice geometric and quite natural way to see that. Now, I don't know if it's so natural. We needed certain calculations of intersection numbers in this Turing. Yeah. But once you have this, you can actually prove that the fine Bergman fan has not more isomorphisms than the ones coming from the matroid world itself. Okay, but you have to use quite fancy techniques. I don't know any more elementary proof of this, but maybe you also want to use these fancy techniques because you are excited that they are here, which is maybe a more honest answer. Okay, but I'm not talking about the proof now in the intersection theory, because I want to discuss with you an example where the fine fan structure is somehow not enough. Okay. So if you're interested in the proof, I should say that the paper is on the archive and also on our homepage. So if you want to read about that, you're very welcome to check that out. Questions?
Is the matroid isomorphism you get from an isomorphism between the Bergman fan unique necessarily?
Yes, this is unique.
I have a question. Don't know if you can hear me from the Zoom. Yes. So does this mean that you can recover the matroid from the Bergman fan with the fine structure?
No, I don't. No, I don't think in general. In some cases we can, but my feeling is that what you are asking is more difficult.
Okay, thank you.
This would mean the question, for example, given two matroids with isomorphic Bergman fans, are the matroids isomorphic? So this, my theorem, so Kris and my theorem would not answer that. In some cases we can actually do so, but I feel that this is a more complicated question.
And I understand what the theorem was.
And let me go back. So you have two matroids, yeah, and you have an isomorphism between their fine Bergman fans. Simple, and of course, and I have to tell, I completely skipped the things here. Not totally disconnected, and this is also important. Okay. Okay, but now let's move on to another problem. I want to discuss with you an example which tells, which somehow says the fine structure does not cover everything which people in tropical geometry find interesting. Okay. So take a root system of type AN. So this is the root living in some n+1 space. Yeah. Sometimes this is also these hyperplanes are also called the braid arrangement. We take these hyperplanes in n+1 space and then we get rid of the line generated by an all-one vector because we want them to have trivial intersection. And these guys intersect, these guys intersect at the line where all entries are equal. We get rid of that. Okay. So we get an arrangement which gives you a matroid. Yeah, as I said, the rank is given by a dimension, codimension of intersection. And it is not hard to see that this matroid is the same as you get when you started with the graphic matroid associated to the complete graph with n+1 vertices. So the K4 we had was in fact the graph, so the graphic matroid associated to K4 was in fact the A3 root system matroid. You can think about it either way. I like root systems, so I prefer that's why I always talk about the other way of setting that up. Okay, this matroid has been, the Bergman fan of this matroid has been studied by many people in tropical geometry because tropical geometry is very successful in these counting problems where people count certain things and often geometrical objects with certain structures in moduli spaces by tropicalizing the whole thing and then counting something tropically in a more combinatorial setting where it's easier to count. And for example, the moduli space of marked curves is something where many people work on. It has tropical avatars. So this space here, there is something which is a moduli space of tropical genus 0 curves. Don't worry if you don't know that, we don't need for this talk, with n+2 mark points. Probably everyone has seen the moduli space when I skip the drop here, yeah. Genus zero curves of with n plus 2 mark points. This also exists in the tropical world. And one doesn't need to understand what this is. The only thing which is relevant for my talk is that if I take the Bergman fan of this matroid associated to Kn plus 1 or the root system, An, it has this interpretation. And in this interpretation, you have a very natural action of the symmetric group in n plus 2 on n plus 2 elements, because it is something with n plus 2 mark points. And of course, you can permute the points, yeah? And you will get a nice action on the moduli space. This is what we do all the time when we look at moduli spaces of marked things. Yeah? Okay, so we have n plus 2x. But on the other hand, the matroid itself, the automorphism group of the matroid associated to Kn plus 1 is Sn plus 1. This is not hard to prove. How do you get an automorphism of this matroid? You take your complete graph and you permute the vertices, which gives a permutation of the edges. And this is the matroid isomorphism. So here there is something going on. The Bergman fan has more automorphisms coming from tropical geometry than the matroid. And this was the starting point of our project because we couldn't understand that. Yeah? So where does that come from? What we wanted to understand is where is the geometry of matroids which gives us the additional transposition, so to speak, we need to generate the full group Sn plus 1 from Sn plus 2 from Sn plus 1. You need one transposition with the last element to get it. Okay, and the answer is the fine fan structure just doesn't do it in this case. We need something which is bigger than automorphism, the automorphism group of the matroid. And in geometry, you find this by considering a coarser fan structure. And the coarser fan structure we need to consider is what people call the minimal nested set fan structure. I think this is the terminology due to Feichtner and Sturmfels, who looked at these nested set structures in a very famous paper. And what is that? So let me explain you what it is, and then we will look at it in an example. In the minimal nested set fan structure, you forget about non-connected flats. Throw them out. I mean, every flat gave you an array in this fine structure. Here you only keep the connected flats. And connected means you cannot, if you restrict the matroid to the flat, it is not a disjoint union of two flats. So there is there's no way of writing your ground set as a union of two subsets, and then independence means that intersection with the first thing is independent and the intersection with the second thing is independent. But there is, however you divide the set E, there's always some interrelation going on. If this is not the case, you call it disconnected. Okay, so in here you throw out the disconnected flats, and you find another way of adjacency between flats in order to define cones. So remember, in the fine structure, a cone was given by a chain of flats. So here we don't use chains. We use what Feichtner and Sturmfels call nested collection of connected flats. So the definition is nested means either things are pairwise comparable, or if not, the closure of the union is not connected. This is a little maybe strange to digest. It's easier to understand what this means if you have only two connected flats. So when do two connected flats give a cone in the structure? So either it is a chain of flats, as we were used to in fine structure, or there's a third possibility now, the closure of the union is not connected. So you throw out the non-connected flats and you define it, you get cones, you write down different codes. Yeah? Okay, let's look at this in an example. K4, again, it's easier to understand in this example. This is our root system, A3, 6 elements has the matroid, and this is the K4 we have seen. So here are the flats with one element. Yeah, it has only rank 3, so we will only worry about flats with one element and flats with 2 elements. The dots upstairs represents the flats of 2 elements, And lines mean this is nested. So this thing is in that flat. So the first flat consists of 1, 2, and 5. 1, 2, and 5. Yeah, this is definitely a flat of rank 2 containing 1, 2, 5. The second flat consists of 1 and 3. 1 and 3. This is a flat. You cannot add anything without increasing the rank, but this is not a connected flat. So this one would have to go if we go to the other structure. This is again fine. This is 1, 4, 6. 1, 4, 6. That's a nice connected flat. It contains 1, 4, and 6. This stays. But the next one is 2 and 4. That's not connected. It would have to go. Yeah. And 2 and 4 would form a cone in our minimal nested set structure. Yeah. Because the union is not connected. Okay, same game here. This is a nice 3-element one. We keep that. This has to go. 5 and 6 has to go. Okay. So what does that give us here? This diagram. This diagram tells you about the adjacency of our fan. So the vertices are the rays in our fan, and when do they form? And whenever they are adjacent, they form the corresponding rays form a rank 2 cone. Okay, so this is the 3-element flat containing 1, 2, 5. That's fine. This is a neighbor of this, and of that, because we have a chain of flats. This is new. 1 and 3, they are both connected, but their union is not connected. So they now become neighbors. And the rank 2 flat 1, 3 disappears. So you have somehow gotten rid of something that was in between here. Same here. This is a nice 3-element rank 2 flat containing this, that stays. But here you again have neighbors. Yeah. And the other pair of elements such that the union is a disconnected flat is that one. So you get rid of some flats and you have new adjacency relations. So this is the new diagram of your cones. The Bergman fan is the union of these cones, but you got rid of something. It's a coarser structure than the fine structure.
Could you refer again to definition? Because
the definition, yes, the definition is you keep the connected flats, and cones are given by nested sets, and the definition is a subset, yeah, is either nested, so forms a flag or flat, or the closure of the union is not connected. So there is an alternative to being nested, yeah, by forming something
but
non-connected.
there are 2 ways of being nested.
Yes, yeah, just because I don't know which is smaller. And if you throw in the ranks, you don't have to worry about them. Okay. This is something, yeah, which is okay. I hope it's clear in the example. Okay, and now we define the following automorphism for the minimal nested set structure of this K4. We look at the spaces. The Bergman fan of K4 lives in the quotient of this space by some line given by the OR1 vector. And I define a very stupid linear map here, mapping B1 to, this is the indicator of the flat B2A, B3. B2 goes to the indicator of the flat B1, C, B3, and B3 goes to the indicator of the map B1, B2. And ABC stay the same. Okay, this is just a linear map. We can push it over to the quotient, and the result is that this does not preserve the fine structure because it's not a matroid automorphism. This thing is not going to a matroid ray, but it preserves the minimal nested set fan. And the nice thing is this is the missing geometric object, because this provides, if you identify the automorphism of this fan with the minimal nested set structure with the Sn+2, which by tropical geometry is the automorphism group of the space, then this thing is the missing transposition, which together with the Sn+1, which comes from the matroid isomorphisms, generates the full automorphism group Sn+2. Okay. And we call this a Cremona. Why do we call this a Cremona? If you look at the hyperplane arrangement A3, you can look at it as something which is contained in P2. And on P2, you have the standard Cremona action. The hyperplane complement of the A3 arrangement is, of course, preserved by Cremona. And now the Cremona, if you take the Cremona automorphism, is an automorphism of the hyperplane complement, and you tropicalize all this stuff in the intrinsic torus, you get precisely this linear map. This sounds so easy, but it took us quite a while to figure that out, because there you have to shuffle the Cremona to a tropicalization in a different torus way. It doesn't look like a Cremona any longer, but it is a tropicalization of an honest Cremona map in P2. And as people know much better than I know, that is the birational geometry of Pn. Cremonas play an important role for P2. They practically give you everything, but in higher dimensions, one doesn't really know how one gets. Okay. So this is identifying the tropicalization of a Cremona map with something which we knew had to be there. Yeah. But this is all in the realizable case. And I mean, it has become very fashionable to go to matroid situations and define stuff just for matroids. And this is now what we did for Cremona automorphisms. So we define something which we call a Cremona transposition for matroids, which, yeah, somehow is a matroid version of this map in the example, which comes from an Cremona. Take a simple connected matroid and take a basis. And then we say the following map, we call the following map a Cremona associated to a basis. This takes the indicator vector of a basis element and maps it to the indicator vector of a co-rank 1 flat, which we get by getting rid of the associated basis vector. So it changes rank and co-rank 1, so to speak. Okay. This is a flat. You have BI is taken out, you take the closure of the rest, and this is the indicator vector of that flat. So the basis goes to co-rank 1 flat, and the rest is unchanged. Okay, and this is a linear map. Everybody is allowed to write on linear maps. And in general, if you take any stupid basis, this will not give much. It need not even descend to our quotient, and it need not even preserve the Bergman fan as a set. Yeah? But we give a criterion for when it does. And the criterion is as follows. Simple connected matroid again, you take B, you endow your Bergman fan with the coarsest possible fan structure. This exists, and it often coincides with this minimal nested set structure, which I have just explained. Often means there is a certain connectedness criterion, which was already formulated by Feitner and Stumpfels, which ensures that. And then we give the following criterion for this stupid Cremona map to descend to the quotient space and to preserve the Bergman fan as a set. And I mean, if it preserves it as a set, it also preserves it as a fan with the coarsest fan structure. This is as follows. Everything in the matroid, yeah, is either an element of the basis or it lies in the closure of two basis elements. This is a very easy to check condition. A matroid need not have this kind of basis. Yeah? But if a matroid has this basis, we call this automorphism of the coarse fan structure, which will not preserve the fine fan structure, a Cremona automorphism of the matroid. And now the question is, how far does this get you? I mean, the question is, how far does this get you when you want to determine the full automorphism group of the Bergman fan with the coarse fan structure, or maybe the minimal nested set fan structure? How far do you get by the matroid automorphisms, which are always there because they even preserve the fine structure, and this Cremona? Oh, that's the question. And we've seen for the matroid given by the braid arrangement, this is enough. I mean, I only showed you A3 just for didactical purposes, but you can play this game in every dimension. And the automorphism group of the coarse Bergman fan, the AN matroid, is always generated by the matroid automorphisms and one additional Cremona, precisely the one we have seen in this argument. And the student of mine checked that this is also true for the other root systems. If you do B, N, and C, and you will have Cremonas, and together with the Matroid automorphisms, they will do everything. In the other cases, you don't have Cremona basis, but in these cases, the automorphism group of the coarse Bergman fan is not larger than the one of the fine Bergman fan, and it coincides with the automorphisms of the Matroid. So in this case, also Matroid automorphisms and Cremonas are enough because there is no more. Okay. So, and it's an interesting question is for which, and as I said, representable matroids, and especially those, this is only almost negligible part of the matroid universe, and it's very interesting to check when this is true. So here's
what do you get for the auto root system? D, E?
So for the other root systems, you check that there is no Cremona basis, but the automorphisms of the coarse Bergman fan are the same as the fine Bergman fan. So it is true.
Yes, but
Yeah.
only for 8 is interesting.
Yeah. Yeah, it's maybe interesting that you don't have more, but you get definitely Cremonas for B and C. Okay, so there's one thing which you have to exclude, where the question is definitely has a negative answer, and this is parallel connections. This is badly drawn because there is an edge here missing. I apologize. I will not really explain what this is, but imagine you have two graphs, yeah, and they collide on one edge. Then you have a new graph. And the matroid associated to the collision graph, yeah, this is the parallel connection of the other two. So here, if this was visible here, you would see that I had glued this one and this one along this edge. I get a new matroid. And one can prove that the Bergman fan of this parallel connection is the product of the Bergman fans. The matroid is not the product, it's a parallel connection, it's more difficult. But of course, if you have something like this, you can do automorphisms here and keep this stable, and you will come with an automorphism here, end up with an automorphism here. There's no chance of coming from a matroid automorphism or a Cremona, which involves the full basis. So this is definitely something which you have to exclude, but this is, yeah, for trivial reasons. Question is, do you have to exclude more? Not in rank 3. That's of course what you do. I mean, you first do a small rank, and you hope, because also in P2, you know, Cremonas, that rank 3 would be okay, and it is. For simple rank 3 matroids, if you exclude just this parallel connection business, which you have to exclude, then the automorphism of the coarse Bergman fan is always generated by matroid isomorphisms, automorphisms, and Cremonas. Yeah. And Kris showed that in an older paper that if you have any isomorphisms between the coarse Bergman fans, then M1 is isomorphic to M2. Now I think I have to come back to the questions we had from the audience. I might have given a perturbed answer, because if you are asking this question about the fine structure, yeah, then the answer is yes, the Bergman fan with the fine structure knows the matroid, but not the coarse structure. Yeah, because not in general. In rank 3 it does, but in the higher rank we don't think that it does. So here this is something, this isomorphism here, so there might be an isomorphism here which does not come from a matroid isomorphism. So you have to be a little, you have to work a little harder to show this thing. Okay, but rank 3 is fine. Okay, what else is fine? This is the last example with which I want to end this talk. And I definitely wanted to have a family of examples which are not representable, because this is always such a scarce thing. So we looked at Dowling matroids. Dowling matroids are matroids you can associate to any finite group and any element n. And it is very easy to define them. You take these n elements, this will be a basis, and you add an element, you add elements for every element in the group and for every pair of indices, which called Gij. So G is the group element, Ij is, so to speak, their location. And then you define now your rank functions by defining the flats. Easy exercise. If you say what the flats is, you can also define the rank function in as follows: Bi, Bj, and all Gij for all G in G. This forms a flat. This forms a flat of rank 2. So this is rank 2. And if you don't want the basis elements, you take two groups, two pairs of indices, but they must have one in common, and the one in the middle. and then you multiply these elements and get rid of the J. So this is the other possible rank 2 flats. The group in general is non-commutative, so you have to take that into account. Okay, so these are the rank 2 flats, and this matroid is what we call line closed. So any flat so a subset is a flat if for any 2 elements the closure of this thing is contained in that. So it's enough to know the rank 2 flats. Okay, so you are mixing a basis with n elements with these group elements, and you get something which is called a Dowling matrix. We have seen this because for the trivial group, this is the graphic matrix Kn+1, so it's the matrix given by our root system An. Yeah? This thing, however, if we are non-Hilbert group, is very rarely representable. It is only representable if over a field F the group G is isomorphic to a subgroup of F star. So as soon as the group is not cyclic, I mean, you will have no representability whatever. And these things can be very complicated. Every finite group, and I mean, there are not so few of them, yeah, every finite group you can think of is the automorphism group of a rank 3 matroid, which is in some Dowling matroid. Even rank 3 is enough, the basis of rank 3 and all these elements. So these all finite groups turn up as subgroups of, as group of automorphisms of submatroids of Dowling matroids. So these things form a huge class, so to speak. Okay, and we show that these Dowling matroids have Cremonas by showing that this basis we use to define this thing is actually a Cremona basis. So it fulfills our property, and we can define the Cremona automorphism of the coarse Bergman fan. So this is yet now a non-trivial example because you have Cremonas, and then we go on and show that every automorphism of the coarse Bergman fan associated to such a Dowling matroid is either coming from a matroid isomorphism or an isomorphism of defined structure, or you get it by composing a matroid automorphism with your Cremona. So in particular, here the automorphism group of the coarse fan structure is generated by this one Cremona the matroid admits plus the matroid automorphisms. And you can generalize this a little further.
This Cremona automorphism, is it an involution?
It's an involution. Yes.
Is that always?
Yes, that's true. If you, this is not so straightforward because it's only true when you divide out this line. But if you take this explicit linear map, which I've given you, and you apply it once more, you see that you get the vector back up to the multiple of the line. Yeah, that's true. Thank you for that question. Okay, so for these Dowling matroids, the answer to our question is yes, and this can be generalized a little bit to a class of matroids which are called modularly complemented matroids. But the Dowling matroids are the most important elements in this category of matroids. Okay, that's all. Thank you.
Questions? Was that one graph you got, the Peterson graph?
Yeah, the Peterson graph was this adjacency graph of the.
It's a counterexample to everything they say.
Yes, that's right. I'm sure there is a reason, but I'm not the person who knows it. No, I mean, I don't know actually, but probably this is because I know too little about the Peterson graph. I just can recognize it. Yeah.
The moduli space of M0 and 5 properlize to a cone over the Peterson graph.
Yes, that's the answer. Thank you.
Can you repeat that?
The moduli space M05 tropicalized to a polyhedral fan, which looks like a cone over the Peterson graph.
And M05 is precisely the A3 thing. And yes, thank you. And this may be a reformulation of my slide, but it sounds like a good answer.
So in this latest example, if you conjugate by this Cremona, you get some automorphism of the group of automorphism.
If you conjugate by Cremona, you get another automorphism of this coarse Bergman fan, but you don't.
The group of automorphism.
Yes. Yeah. And this will. I mean, it will depend on what that is. I mean, if you only have one, this is easy to study. In the AN case, you can, if you conjugate one Cremona by another, you can, yeah, you have several Cremonas, and there. It's not always, what I'm saying is this will not always map certain automorphisms to automorphisms of a certain type. Yeah. But of course, this is a way of investigating the situation.
Thank you. Thank you for your talk. I was wondering, does the tropicalization of the complement of a hyperplane arrangement give you a natural fan structure, or does it just give you the set structure?
I don't think it gives you a natural fan structure, because I mean the topic, if you, so I would say in rare cases it gives you a natural fan structure, but not in general. Just gives you the set, and then you have to endow it with fan structures. I mean, Shio, would you agree that there's no natural fan structure?
I don't know.
Yeah. So I don't think so that you can call this natural. Yeah, you will usually just investigate several fan structures of that. I mean, there are several interesting ones who do different things. People might say the coarsest is almost the natural. I don't know.
Yeah.
But people are asking for one which is defined in terms of tropical geometry, and this I don't know.
Okay. Thank you.
Does this answer your question? Okay.
Yeah, I guess I was wondering where the motivation for these different fan structures comes from, if not from tropical geometry. So for example, the fine or the coarse.
Yeah, so for us, it really came from tropical geometry.
I see.
Question, yeah. Michael, ask your question.
I'm sorry.
What is Cremona automorphism of hyperplane arrangements? Looks like someone who doesn't know any birational.
So I'm saying that if you have a hyperplane arrangement, so we have one. So in our situation, in our example, the hyperplane arrangement was one such that the Cremona of the plane preserves.
What does this mean? This is my question. What is? I don't know any algebraic geometry.
Okay. So in the Cremona is a birational map. It has a certain locus where it's defined and where not. And this example I was showing to you, it was defined as really an honest algebraic geometry map on the complement of the hyperplane. So it is not defined in the PT, it's not defined on the hyperplanes where one coordinate is 0. Yeah, and in my situation, when you get rid of this linearity space, you are in this situation. So the complement is a nice subvariety on T2, which is honestly mapped to another one.
How does it work? What is the map?
What is the map? So the Cremona in this situation, you have projective coordinates, and you would map it like this.
Okay.
So of course, other different ways to define it.
Like another stupid question: why does this not go down to the Matroid?
Pardon?
Why does this automorphism not go down to the Matroid?
Why does this automorphism?
Why does it not go down to Matroid automorphism?
Yeah, because when you see it the way we rephrased it in coordinates, I mean, if things go down to a Matroid automorphism, they must map an indicator vector of an element of a Matroid to an indicator vector of another element of the Matroid, because this is how a Matroid map gives you an automorphism of the fan. Yeah? This our fan structure has rays for every flat. Yeah? And here this maps a rank 1 flat, the indicator vector of the rank 1 flat, to an indicator vector of a co-rank 1 flat. So then you know, it is not induced by the process, okay, we have a Matroid isomorphism, what do we do on linear algebra? Map the indicator map of the element I to the indicator map of the element J if they are connected by the Matroid. This is not the case here.
That's my question is, are there some automorphisms of the hyperplane arrangement that do automatically go down to the Matroid? So I'm not understanding it at all. I'm very simplistic.
Yeah, so this is so asking about the geometry of the hyperplane arrangement is even a third thing. Yeah. So I have talked about automorphisms of matroids, automorphisms of certain fans with fan structures, asking about algebraic geometry of this hyperplane arrangement is the third thing. There are relations, but there are also examples which show that this can be much more complicated.
Sure. I'm trying to understand.
Yeah, I'm very happy. I'm just not sure if I'm answering your question in a helpful way. So tell me.
I got something.
Yeah.
Okay, let's thank Annette again.